My previous videos described the DFT in detail for only one-dimensional signals, but I showed a few 2D image examples along the way. Today's video will concentrate on the multi-dimensional DFT for images and volumes. I'll also discuss the concept of the Fourier power spectrum and show you how it's calculated. Many of the illustrations and image processing examples in this video were done with the free and open source BIPS software. See my introductory video on the BIPS for instructions on how to download and install it. Although you've seen me manipulate 2D harmonics before, such as in this demo of Fourier synthesis from my first Fourier video, and so you probably have some intuitive idea of what a 2D sinusoid looks like, in this section I want to define the multidimensional sinusoid in more detail, so you can understand its component parts and how it's represented in a multidimensional Fourier transform. If we take this 1D wave, represent it as a grey level plot, and simply copy it unchanged along the second dimension, we get a 2D wave that looks like this. Here the frequency of variation in the y direction is 0, because there is no variation in the y direction. However, the frequency in x is 3, because the values fluctuate through 3 complete cycles along the x direction. Now here's the same 1D wave we started with before. I will again make copies of it along the y direction, but this time, as I duplicate it, I'll vary the value of each pixel in the copy in a sinusoidal way as we go down along the y direction, and I'll do this variation with a frequency that is specific to the y direction. In this example, I'm using a y frequency of 2. So the result is a 2D wave that has a frequency in the x direction of 3, and that is the same frequency all the way down. But at the same time, it also has an amplitude fluctuation in y at a frequency of 2, and this is true for all vertical scan lines at any x position. So you see, in general, a 2D sinusoid is composed of 2 orthogonally independent frequency components, an x frequency and a y frequency. Because the components are orthogonal, we can vary the frequency in one dimension without altering the frequency in the other. Now we move on to phase in 2D sinusoids. Note that the starting point in the cycle, that is the phase, for each wave along a column in the y direction is dictated by the pixel at the very top. In other words, it is the phase of the pixel in the first row x wave. So when this x wave pixel is a crest, the wave going down in y begins at a crest, and when this x wave pixel is a trough, the wave going down in y begins at a trough, and so on. This tells you that while the frequency of the x and y components are independent, their phases are related to each other. Here is an animation of the 2D sinusoid where the phase is shifting and cycling over the whole 2π range. Finally, note that although the frequency components are different in x and y, this 2D wave has a common amplitude, something I'll discuss a bit more in the next section. I can explain 3D sinusoids in a similar way. So if we take this 2D sinusoid and replicate it in the z direction without altering the copies, the result is a 3D sinusoid with a z frequency component of 0. But if I vary the intensity of the pixels in the copies of the 2D sinusoid as I stack them up, then I get a 3D sinusoid with a non-zero z frequency component. From my previous videos, you'll know that at each frequency, the DFT specifies just 2 numbers, the Fourier coefficients for that frequency. And these 2 numbers define 2 specific harmonic waves, one for reconstructing the real component of the input signal, and one for reconstructing the imaginary component. Another way to look at this is to say that each single harmonic wave, at a particular frequency, is completely specified by only 2 numbers, the Fourier coefficients. As you'll see in the next section, this situation does not change at all for Fourier transforms at higher dimensions. That is, the 2D DFT and the 3D DFT still only output 2 numbers per frequency. So how can only 2 numbers, the 2 Fourier coefficients, completely describe a 2D or a 3D wave? The answer is that each wave, regardless of its dimensionality, can be described by a single one-dimensional resultant wave. Because this resultant is always a one-dimensional waveform, it has only one amplitude and one phase. The Fourier coefficients therefore specify the phase and amplitude of this single resultant 1D wave at each frequency. You can construct the resultant wave by simply taking a straight scan line through the wave starting at the origin point and traveling in a direction perpendicular to the wavefronts. The values of the original wave along this line can be plotted to form a single one-dimensional wave, regardless of whether the original wave was one-dimensional, two-dimensional, or three-dimensional. So, the Fourier coefficients define the amplitude and phase of this resultant one-dimensional waveform in a DFT of any dimensionality. Note that in these resultant waves, the frequency, that is the total length and number of troughs and crests in the wave, are irrelevant to this point because the frequency is determined solely by the position of a pair of coefficients in the transform and not their values. The coefficient values only determine the amplitude and phase of a waveform. So, how do we do the DFT in 2 dimensions? Well, the formula looks like this, but in practice what this boils down to is that for a 2D image you perform a series of one-dimensional Fourier transforms on the rows and arrange the results as rows of complex Fourier coefficients, and then simply use the complex Fourier coefficients from each column of this array as input to another forward DFT, and you do this for each column. So you do a series of 1D forward DFTs on each column. The end result is a grid of complex coefficients that represent the full 2D DFT. A 3-dimensional image can be seen as a stack of 2D images. So, to do a 3D DFT, you convert your stack of 2D images into a stack of 2D DFTs, as explained previously. You then do a forward one-dimensional DFT on each Z column of complex coefficients from that stack. The resulting 3D array of complex Fourier coefficients is your 3D DFT. So, multidimensional DFTs can be formed by sequential application of the one-dimensional DFT along each dimension, and the order in which the dimensions are processed makes no difference to the end result. Mathematicians refer to this property as separability, that is, separability of the dimensions. For the rest of this video, I'll be using 2D examples for brevity, but you should be able to figure out how those 2D examples would extend to 3D volumes. Here's an example of a DFT performed on a 2D image. These are the real components of the Fourier coefficients, and these are the imaginary components of the Fourier coefficients. In both cases, the values of the coefficients are represented as images, with the gray level being proportional to their numerical value. In the Biochem GUI software, which is part of the BIPS software, the values of the real and imaginary coefficients are displayed in these boxes. They show the values of the coefficients which your mouse cursor is currently over. Over here I've made a montage of all the actual 2D harmonic waves defined by the Fourier coefficients for reconstructing the real component of the input image. There will be another set of waves for reconstructing the imaginary components of the input image, but I'm not showing those here. Note that there is one wave per pixel position in the DFT. I've arranged it so that the relative position of the waves are the same as the position of the coefficients in the DFT that define them. As with any Fourier transform of any dimensionality, the frequency that any coefficient relates to is determined by position in the transform of that coefficient. In this respect, note 3 things. First, in this case, all coefficients to the left of the vertical midline will represent negative x-component frequencies, and to the right side they will be for positive x-component frequencies. And all coefficients above the horizontal midline will be for representing positive y-component frequencies, and all those below that line for negative y-component frequencies. Secondly, points exactly on the midline in x represent frequencies with an x-component of 0, even though the y-component of the frequency along this line can be anything. The converse is true for points along the midline in y. The point that is on the midline in both x and y, that is the center point, represents the zero-order harmonic, that is the DC offset for the whole image. Third, the further from the center you go, the higher are the absolute frequencies represented by the Fourier coefficients at those points. In this example, our input image is real and non-symmetric, so as I explained in my previous Fourier video, we expect the Fourier coefficients to have Hermitian symmetry, and this is in fact the case. Note that the real coefficients show even symmetry, with the values of the positive frequency coefficients being exactly the same as their equivalent negative frequency counterparts, and the imaginary coefficients show odd symmetry, with the positive frequency values being the inverse of their negative frequency counterparts. Now, some of you who may have seen other Fourier transforms of images might be thinking, but this doesn't look like the Fourier transforms I've seen before. The reason for that I'll discuss next. The reason the DFT in the previous section didn't look like the ones some of you might have expected is that most people, when they display a Fourier transform, don't display either or both the Fourier coefficients. Instead, they display a plot which captures the absolute strength of each harmonic in just one number per harmonic. Not only does this mean you don't have to switch between two components like this all the time, but also it gives an instant visual sense of how strong or dominant a particular harmonic is in comparison to all others. This overall measure of strength of a harmonic is called its power. The power of any sinusoid is equal to its amplitude squared, so power will always be either positive or 0, unlike the Fourier coefficients, some of which may be negative. This is because the Fourier coefficients convey a degree of correlation of a sine and cosine with your image data, and correlation may be positive or negative, as I explained in my first Fourier video. We calculate the power using the Fourier coefficients and considering them as vectors on the complex plane. When we do this, the resultant vector has a length that is equal to the amplitude of the wave the coefficients represent, and the angle made by the resultant vector to the real axis is the phase of the wave. So you see, my analogy of basis vectors from the previous Fourier video was actually more directly relevant than it might at first have seemed. So, by using simple trigonometry and Pythagoras, we can represent the same information conveyed by the two orthogonal Fourier coefficients into a wave amplitude value and a phase angle value. It's tradition, when doing this conversion from rectangular to polar coordinates, to relabel the amplitude as modulus or magnitude, and the phase angle as argument. So you might hear me use these terms interchangeably. So based on the definition of power as amplitude squared, you can see that the magnitude is the square root of the power value. Here on Biochem you can perform this translation to polar coordinates by simply clicking this button here for magnitude values and this button for argument values. So this is the magnitude spectrum, showing the magnitude of the resultant wave at each frequency component, and here is the argument spectrum, showing the phase angle of the resultant wave at each frequency. If we turn on the angle indicator of Biochem by clicking this argument button again till its label font turns red or green, then this line will point in the direction dictated by the phase angle of whatever pixel the mouse is currently over, so you can get a graphical sense of its argument value. You can also see the magnitude and argument value of the pixel your mouse is currently over expressed directly as numbers in these text boxes. Returning back to the magnitude spectrum view, to turn this into an actual power spectrum, we need to square these numbers, and you can do that like this. So this is the power spectrum of the Fourier transform of the image. For those of you who have downloaded my Fourier spreadsheet that I described in a previous Fourier video, this sheet here will show you a plot of the phase and power spectra of whatever signal you program into it. In many images, the central lowest frequencies, and especially the very center DC component, will have a much higher power value than the more peripheral higher frequencies. So in order to visualize the contribution of the higher frequencies in visual displays of power spectra, intended for human viewing as opposed to calculations, it's common practice to show the logarithm of the power rather than the power itself. You can do that with Biochem like this. However, I find it quicker and easier to simply view the logarithm of the magnitude spectrum, if all I want to do is have a visual impression of the power spectrum without having to go through all the procedure for calculating it. Both the magnitude and the phase values are essential to fully define the correct harmonics for Fourier synthesis. In fact, they are an alternative pair of defining numbers to the real and imaginary Fourier coefficients. For certain mathematical manipulations, one or other type of representation may be advantageous. Because it's so common for people to display image DFT information as magnitude or power spectra, it might cause some people to think that this aspect of the polar coordinate values is somehow more important than the phase. This is very much not the case. In fact, in some respects, the phase spectrum is more important than the magnitude or power spectrum when it comes to reconstructing an image from its DFT. This is because it is the argument data that gives us spatial information about how the harmonic waves are deployed across the image. Let me give you an analogy in the case of an image and its histogram. The histogram shows how many pixels in an image have a certain gray level, but it doesn't tell you anything about where those pixels are located in the XY grid of the image space. However, it can seem to do so in some cases. Consider this image of an MRI of the head and its histogram here. You can see that the histogram has 4 peaks, and we can relate those peaks to spatial regions in the image. So this peak at the very dark end represents this air space around the head and in the oral cavity and sinuses of the skull. This peak of very bright pixels represents the whitish regions in the image, such as the subcutaneous fat and the fluid regions in the vessels and bone marrow. Finally, we have these 2 peaks, one for slightly darker pixels and one for slightly brighter pixels, and these can correlate to the grey matter and white matter of the brain. However, consider that all the pixels in this image are like square jigsaw pieces arranged in a grid. If I take all those pixels, put them in a box, give the box a shake, and then randomly pick out pixels and put them back into the same dimensional grid but in a random order, then we get this scrambled image. But because we're using the same pixels without changing their number or gray levels, the histogram of this scrambled image is exactly the same as the one we had before. This emphasizes that the histogram just gives us a kind of magnitude spectrum for gray levels and contains no spatial information at all. You can't reconstruct the original image from this scrambled image just from the histogram data alone. Likewise, you can't synthesize an image from its magnitude or power spectrum alone, without the phase data held in the argument spectrum. To demonstrate this directly, I've made the DFT of this image of a cat, and here are the magnitude spectrum and argument spectrum. Below, I show what we get when I do an inverse DFT, using the exact same magnitude spectrum data, but with different options for the argument data. First, if we use the original argument spectrum from the DFT, we get a perfect reproduction of the cat image, as expected. Next, I replace the original argument spectrum with uniform phase values, here with all the argument values set to 0, and here with all the argument values set to pi. In both cases, the resulting image looks nothing like a cat, even though the power spectrum is exactly the same as for the original cat image. To make things a bit more interesting, this third image is what you get if you use the original argument spectrum values, but with all those values scrambled in position compared to the original. Again, it looks nothing like the true image. Finally, this is what you get if you perform a phase transplant, using this MRI image as donor. So this uses the original cat image magnitude spectrum values, but the argument spectrum is that of the DFT of this MRI image. You can see that the result looks distinctly more like an MRI brain than a cat. So, to use a biological metaphor, if the phase and magnitude were morphology gene alleles in a heterozygote, the phase would be the dominant allele, at least in this example. I now want to show you some basic image processes that can be done using the DFT. One of the things you can do very easily in the Fourier domain is scale an image in size. This works thanks to the dependence of frequency on n, the number of data points in the signal, which I described in my second Fourier video. To briefly recap, the unit of frequency in the DFT is n, which in the case of a 2D digital image represents the number of pixels, and we can divide this into nx and ny for number of pixels in width and height respectively. So, if you have a frequency in the x direction of 2 in an image that is 8 pixels wide, then a harmonic at that frequency makes 2 complete cycles in those 8 pixels. Now, if you have that same value frequency 2 in an image that is 16 pixels wide, the harmonic has more pixels in which to make the same number of cycles. So it is effectively stretched or enlarged in width, and the same can be said for frequencies in the y direction and stretching in height. Thus, to make an enlarged version of an image, simply take its DFT, pad the DFT with zero-value coefficients to the desired end goal, height and width, and then do an inverse transform of this bigger DFT. The result will be a bigger version of the image, because we didn't change any of the values of any of the frequencies, we just gave them more room to perform their cycles by increasing nx and ny. Conversely, you can shrink an image by simply cropping its DFT to the desired smaller size. Let's take this example image and forward transform it and look at the magnitude spectrum. We know that the highest frequency harmonics are represented at the periphery of the spectrum. So let's see what happens when we set those Fourier coefficients to 0, which I'll do with this circular mask. Every Fourier coefficient under the mask I'll set to 0, like so. Now, when we back transform, you can see that the result looks blurry compared to the original, because we've lost the detailed definition that the high-frequency harmonics provide. So now let's do something similar, but at the other end of the frequency scale. This time I'll nullify the centralmost frequencies that represent the overall intensity and gradually changing structure, using a central mask. The inverse transform shows that now we've only got the detail, like sharp edge transitions, but very little in the way of preserving overall brightness across the image or across large regions, which is what the lower frequency harmonics provide. Here's another image made with a printer that can only use black pigment, but it gives the illusion of shades of grey by changing the relative size of the black dots on a regular grid pattern. This technique is called half-toning by pulse width modulation. Because the grid pattern of dots is regular, it means it's also highly periodic, so we can expect characteristic peaks of power in the DFT spectrum for the frequencies that are at or around this regular dot grid frequency. And indeed, the Fourier transform magnitude representation shows those peaks very nicely. Now, if we make a mask to cover those peaks, and here's one I made earlier, and we set to 0 all Fourier coefficients under that mask, like so, then, if we inverse transform the result, you can see that the strong periodic pattern of the dithering dots has been removed, and our filtered picture now has true shades of grey instead of the black and white dithering pattern. Now, this all-or-nothing hard-edged thresholding of the Fourier spectrum is not the best way to remove this pattern. Better results can be achieved with more subtle and sophisticated Fourier coefficient adjustment. But this simple setting to 0 under a mask method is easier to demonstrate for introductory purposes, and this video isn't meant to be a masterclass in frequency domain processing. I just used these simple examples to illustrate the layout of the Fourier coefficients in a 2D DFT. In this video, you've seen how easy it is to extend the DFT to 2 or 3 dimensions due to its separability property. I explained how the Fourier coefficients can be seen as rectangular coordinates that specify a harmonic wave, and how we can transform those into polar coordinates to get the same defining information, but in the form of magnitude and argument values, which represent the wave's amplitude and phase, and how magnitude squared is called the power of the harmonic. Finally, I gave a few simple examples of image processing in the frequency domain. More advanced Fourier image processing techniques will be covered in future dedicated videos. If you like this video, please hit the thumbs up like button and view some of the other videos on my channel. If you'd like to support the project, you can do that by subscribing to this channel and telling others about it. If you'd like to help me continue this work, take a look at my Patreon page, where you'll find additional content and early bird access to future videos. Thanks for watching.